That is our second seminar. It's about nonlinear strain, strain measures, related stress measures, and the identification of the force density. Let's start to understand what we mean by theory of first order. And I take the beam as the reference structure to recall what you have learned in your basic courses. Let's look at this beam between two supports loaded by a lateral distributed load, and we observe the deflection as a function of the longitudinal coordinate x. Then the nonlinear complete curvature of this beam is this formula which any mathematician would tell you. It's quite obviously nonlinear as a function of the second derivatives of the deflection, and also you see here the first derivative of this deflection. Let's now apply the simplifications of theory of first order. That means in particular that we have small rotations. So the rotation assumed to be very much smaller than 1. And with this assumption, it just appears that we can take the negative rotation as equal to the first derivative of the deflection line W. And if we just apply this simplification, that W prime is equal to phi, and phi is very much smaller than 1, you see that we can neglect the W prime squared, which becomes even smaller against 1. So we can take it out of here, and we receive that information where I'm sure almost that everybody of you knows that the curvature of the beam is the negative second derivative of the deflection line. That's exactly what we use in theory of first order. Yeah, so we can write kappa equal to minus W double prime. A further approximation, which comes from the assumption that the rotation is very much smaller than 1, we can say approximately we can take everywhere the cosine of the rotation approximately to 1. And also we can take approximately that the sine as a tangents of phi is equal to phi. These are the typical simplifications of theory of first order. And in particular, this simplification, this approximation creates further problems if we stick to theory of first order going into large deflections. Let's now go to our cables, our cable net at the very end. And let's just observe what happens if we just apply loads. We have this simple mind experiment, one cable between the left and right hand support, the typical situation in your garden when you, after washing, just dry your clothes in the fresh air. And everybody knows from experience that we immediately observe really large deflections if we load it in by a wet shirt. Let's model that in our terms. There we have the left support, right support. We simplify the cable links to the right and to the left by this straight line here, and we apply the force here at the center. And that's exactly what we observe with quite large rotations here to the left and to the right. From symmetry in this little example here, we observe immediately that the horizontal deflection of this center node here must be 0, as I said, from symmetry. Next is that we can just decompose the load into the two cable forces to the left and to the right, which again from symmetry must be the same. Then we can take away the right side and reduce our analysis to the left part of our structure. Again, we observe the large rotation, not small anymore, very large rotation phi, and we observe the initial length of our cable link and the deformed length L0 and deformed L deformed. Quite obviously, from the triangle, L must be longer than L0. Let's now introduce our simplifications from theory of first order. In particular, that one here. As I said, along theory of first order, we assume that the cosine of phi remains constant and 1, which means that we just assume that the rotation is 0, which quite obviously is not the case. But let's neglect that first of all. Let's apply Hooke's law for our linear spring, and you just remember this basic relation between the cable force and the elongation u, and the stiffness which we had from there. Let's now introduce what we see from the left-hand side together with the assumption phi equal to 0, then the u, the deflection in the original horizontal direction is 0. And if you just go further, the result will be applying theory first order. No matter how large the rotation is, we always will receive s equals 0 quite consequently if we just go along these assumptions and simplification. Obviously completely wrong. And what is the reason of that? The reason of that this assumption of what we call of the linear strain, that is obviously wrong. That must be replaced, and that's exactly its solution. We are just replacing these assumptions of what we call the linear strain together with linear theory of first order by nonlinear strain measures. For instance, as an example, we can take that one here, which we call the Green-Lagrange strain, which is now a function of the lengths deformed and undeformed squared, as displayed. And if we take this term for the strain and again put it into our Hooke's law, we can just receive what is called the Piola-Kirchhoff force of second kind as a function of the Green-Lagrange strain, the elastic modulus, and the cross-section of the undeformed cable element. That's already the solution, how we can approach nonlinear problems, and everything would be fine. Next is, let's look into pre-stress and initial length. Coming back to our little experiment here, I'm just loaded by our wet shirt, and eventually the cable might be not stiff enough, and when the deflection is too large and the clean, freshly washed shirt might just hit the ground. That's of course nothing what we like. What is the solution? Solution, everybody knows, is just to apply pre-stress to the cable and by that reducing the deflection. So what are we doing? We go back, take a cable a little bit smaller than the distance between the two supports and just force it by pre-stressing it or pre-deformation. We elongate it into the supports. We apply by that a pre-stress force. As a consequence, the deflection might be smaller and everything is fine. The shirt doesn't hit the ground anymore. Okay, let's go back to our model. That's our model. You see, we just take the length of our cable a little bit smaller, and as we just divide it into two pieces, two parts, because in the center we will apply the force. We just concentrate again here to the left side. We will just observe the initial length, the initial undeformed length, L sub 0. Then we apply our pre-deformation. We call that U sub 0. Again, just for the left side, and you can imagine that we have the same for the right side. Due to that, we just introduce a pre-stress force S sub 0. Again, the stiffness value is elastic modulus times the cross-section A, and that exactly is the nonlinear Green-Lagrange strain, a little bit separated into a linear part and into a quadratic part. So that is the pre-stress force which we have to consider further on. And with respect to our previous seminar, that would be the S with the under comma. Okay, let's now look in our pre-stressed model here. We have just closed here the gap to the right support, and we observe now the initial length and the pre-deformation, the pre-displacement U sub 0. Then we observe the final deflection, and in this sketch you see everything what is of importance. The deformed length, the applied load, the undeformed length, and the pre-deformation U0. And if you go to determine the Green-Lagrange strain, then that one is the deformed length, this one is the undeformed length, and by that we just automatically consider the pre-deformation U0 to receive the pre-stress force. Straightforward, there are also alternative strain measures. We just have learned about the Green-Lagrange strain. Here it is, we repeat it. That one we just take to replace the linear strain, which we know from theory of first order. But other than the Green-Lagrange strain, there are other alternatives which just do the same job. They make us able to analyze large deflections. There are the Euler-Almanzi strain, the engineering strain, the logarithmic strain, and we can also take the deformation gradient as a strain measure. You see the differences are in this case here that we replace the initial length by the actual length here in the denominator. Here it looks pretty much identical to what we have learned from theory first order. The difference, however, is if we look here at the engineering strain, that the deformed length and the undeformed length are measured in different directions. The undeformed length horizontally and the actual length in this rotated orientation. That makes a difference to theory of first order, where we assume that all these lengths, or both these lengths, are measured in the same direction. You see it pops up that we assume phi equal to 0 in theory of first order. If you just look what you receive for all the strain measures, but the deformation gradient, that's the exception. If you just look at these guys here, and you substitute L equal L0, that means the deformed length remains the same as the undeformed length, then you see this difference is 0, here as well, so we receive 0 here for the strain. And if you substitute here for the logarithmic strain, also L0, you receive the logarithm of 1, which, as you know, is also 0. That's a quite natural understanding of strain, such that there is no deformation, the length remains the same. Then, of course, straightforward, there's also no strain. However, if you look at the deformation gradient, it pops up here as well. Then we have here the ratio of 1. And indeed, the deformation gradient is 1 if there is no deformation. In the sequel, we will now concentrate on these two alternatives, the Green-Lagrange strain and the logarithmic one. And we will see in a second why we do that. As there are strains, there are also stresses. Think of Hooke's law, sigma equal to elastic modulus times the strain. And as quite obviously we have now several alternative strains, then there are of course also related alternative stress values. Starting at the top, that's the standard theory first order, where we have linear strain. Then we have also what we call first order stresses or stress. The related value to the Green-Lagrange strain is what we call the Piola-Kirchhoff stress of second kind. I've mentioned that already. The Euler-Almanzi strain is related to what we call the Cauchy stress. That's, by the way, is the true stress. The stress what you will receive by dividing the actual force in your cable by the actual cross-section, which by the Poisson effect will be different from the initial value. That is the Cauchy stress. The related value for the engineering strain is what we call the Biot stress. The logarithmic strain comes together again with the true stress, the Cauchy stress. And what is related to the deformation gradient is what we call the Piola-Kirchhoff stress of the first kind. It's quite obvious if you start with the second kind that there must also be a first kind. Here it is. These are the pairs of strains and stresses which all can be taken for the completely nonlinear geometric analysis. And as there are different stress measures, there must be also possibilities or a rule to transform one stress measure into the other one. And that goes along the virtual internal energy, which we receive from a body in 3 dimensions, just by integrating over the body the product of the stress at the point times the virtual strain at that point. And let's look into 2 alternatives, with the Piola-Kirchhoff stress second kind and the virtual strain in terms of Green-Lagrange. And there in this case you have to integrate over the initial volume, the initial volume, the initial length times the cross-section, the initial cross-section. And if you just take the pair of Cauchy stress and the logarithmic strain, it looks like that with the virtual logarithmic strain, and we're integrating over the actual volume. Here it is, so we're integrating over the reference volume, in this case, with the cross-section, the undeformed cross-section capital A and the initial length. We can do that for our cable. We are reducing everything now to our cable, that along the length of our cable, everywhere we will have the same stress, and everywhere we will have the same strain and the virtual strain. So that is already reduced to our specific cable problem. And on the right hand side, equivalently, we have the true stress and the virtual logarithmic strain, everywhere constant, everywhere the same value along our cable, and we have to integrate now over the actual volume with the actual length and the actual cross section, which we'll call now small letter a. Straightforward. And since no matter what kind of stress and strain measures we take, the energy should always the same, or the virtual energy as well. That's exactly the physical principle behind that. No matter what kind of measures you take, or for every measure you may choose, the value for this, the energy, or in particular the virtual energy, should be the same. Let's now substitute what we had found or defined for our strain measures. Here, the Green-Lagrange measure as introduced before. Then the virtual strain we can just again determine by the chain rule, looking at this value which might be varied. The initial length is a constant number which will be the same throughout the complete deformation history. So the deformed length, that's what is variable. So taking the derivative with respect to the deformed length, we receive 2 times L over 1/2. So the 2 just drops out. L over L0 squared post multiplied by the variation of the length, the little value we just play around, changing the length. Substituting that again, and over here in this integral, we receive the virtual internal energy as the undeformed cross-section value A, the Piola-Kirchhoff stress of second kind, and that we just receive from here the variation of the strain. And you see just one L0 just may cancelling out. If we do that, and then what remains is A times sigma, which is the force, in this case the Piola-Kirchhoff force of second kind. And you have this ratio L over L0, which is remaining times the variation of L. And we observe again, the deformation gradient just pops up. Now that is really one of the basics of nonlinear continuum mechanics, that everything at the very end can just be reduced to these ratios of deformed and undeformed configuration, as we said, in terms of the deformation gradient. Okay, let's do the same operations here on the right hand side. So we introduce the logarithmic strain as we have seen it on the previous slide. The logarithm of the deformation gradient. The virtual strain is again applying the chain rule, derivative of strain times delta L, and just the derivative of the logarithm here with respect to the deformed length is just 1 over the length, and that is finally the virtual logarithmic strain. Substituting that in our integral here at the top, we receive this result. And you see again A times sigma, in this case the Cauchy stress is the force, the Cauchy force S sub C post multiplied by the variation of the length. Again, we just recognize what I said before, that the Cauchy force is indeed the true force which we measure in the deformed configuration where the cross-section had been reduced by Poisson effects, at least eventually. On the left side, we identify the Piola-Kirchhoff force of second kind as a term which remains constant throughout the complete deformation. Capital A will not change, that's the initial value of the cross-section. And the Piola-Kirchhoff stress of second kind is also something which we just identified as something which will not changing throughout the deformation. So that's why we call the Piola-Kirchhoff force of second kind also the reference force S sub 0, something which is defined in the reference state and which will not be changed anymore throughout the complete history. Okay, now we identify that we should have the same value on the left side and on the right side, that the virtual internal energy remains, of course, the same no matter what measurements we take. And then we can take this equal to that, we just repeat it, taking the reference force here in this notation and the actual force in this notation. And you see the delta L just drops out, and we can reorder what we see on the left hand side, and you see we just receive this ratio of the reference force over the reference length. And just remember, what is that? Yeah, that's exactly the force density. That's the force density Q, which in the force density method is assumed to be constant throughout the complete deformation, as it is indeed the ratio of two values coming from the reference state, that means the undeformed state. We can substitute here for Q, and then we just receive this relation Q times L equal to S, which indeed is the true force after form finding when we substitute here the deformed length L, multiplied with the given force density. And furthermore, we can state that the force density is the ratio of the reference force over the reference length, but also look at this one here, the ratio of the actual force over the actual length, which tells us that again that the force density remains constant throughout the complete history of deformation, because simultaneously the actual force is modified together with the actual length by the same scale. And furthermore, coming back to what we see here, the force density is indeed equivalent to the Piola-Kirchhoff force of second kind, or respectively the stress. If we come back to the definition of the force as cross-section times stress. And that, as a consequence, is the entry point to extend the ideas of the force density method to the form finding of membranes, where we take, instead of the force density initially defined for cables, the Piola-Kirchhoff stresses second kind, which straightforward can easily be extended to two-dimensional stress states, as it is the case in membranes. And the further step would be the updated reference strategy, which on this basis we just are able to determine minimal surfaces. We already come to the summary of this seminar. We had introduced nonlinear strain and stress measures necessary to be able to do nonlinear large deflection analysis. We had introduced what is called the deformation gradient F as a ratio of the actual length, the deformed length, to the undeformed length, which is taken or used to map between those measures. And we have found that the force density Q is equivalent to the ratio of the Piola-Kirchhoff force of second kind and the undeformed length L0. The force density and the Piola-Kirchhoff force of second kind are defined with respect to the undeformed reference configuration. We see it here. Both of them are defined with respect to the undeformed configuration, which means directly that the Q, the force density, is also defined, first of all, with respect to the undeformed configuration, and important to realize it remains constant throughout the complete deformation history. We had introduced the understanding of what is the Cauchy force S sub C as what we call the true force. By the true force we mean the product of the true stress times the true cross-section. Remember that the true cross-section might be different from the initial cross-section by Poisson effects. And that means that the true force is of course related with respect to the deformed configuration. And then we have the two force measures, the Piola-Kirchhoff force of second kind related to the undeformed configuration, and the true force as Cauchy, the Cauchy force, and they just map by the deformation gradient. Though these are important findings, which first of all tell us that the force density is really a completely consistent number in continuum mechanics. There's nothing special to that, nothing heuristic. It's really a mechanically defined term, and that makes us able to come to the next seminar, number 3, to go now into the force density method and to understand it really as a part of mechanics. We have now done the first 3 seminars, 0, the introduction, the first and the second seminar, and that will be the next one, number 3, and we will now look carefully into the force density method. Thank you.